So in this part, we discussed about correlation, type of correlation, methods of studying of correlation, Karl coefficient of correlation, rank correlation, then after regression, and types of regression, methods of studying regression, regression coefficients and property, and property of the lines of regression. Okay, so here you can see that two major part of this unit is correlation and regression. Okay, so correlation is and regression is what? It is nothing but represent of relation between two variables. Method of representation of relation between two variables. So let me see what is that. Correlation and regression are statistical methods that are commonly used to compare two or more variables. For example, comparison between income and expenditure, price and demand, etc. Correlation measures the association between two or more variables and quantitates the strength of the relationship. It evaluates only the existing data. Whenever regression means average relationship between two or more variables, and this relationship is used to estimate the most likely values of one variable for specified values of the other variable. Okay, so in simple meaning, using correlation and regression, we can represent relation between two variables, okay, or more than two variables. And what is the major difference between both of them? Correlation evaluate only existing data, whenever in regression represent first of all average relationship, and using regression you can find out the value of some specified data using some given data. Okay, so this is the major difference between both of them, and generally both is term represent the relation between two or more than two variables. Right. So let's start with correlation. So as we discussed, correlation is what? Correlation is the relationship that exists between two or more variables. It is a statistical measure for finding out the degree or strength of association between two or more variables. Two variables are said to be correlated if change in one variable affects a change in the other variable. Such a data connecting two variables is called a bivariate data. We already discussed what is bivariate data in unit number 1. Okay. And how can we identify that this is a correlated data? If one variable affect change of one variable affect to change of other variable, then we can say that both are correlated. And this kind of data is known as a bivariate data. Thus, correlation is a statistical analysis which measures and analyzes the degree of extent to which two variables fluctuate with reference to each other. Some examples of this relationship. First one, relationship between height and weight, relationship between age and strength of a body, relationship between temperature and rain. Okay, so in three of the example, you can see that if you change any one of the variables, suppose you change height, okay, and obviously there is some change in weight. If our age will increase, okay, so after 40 or 50 our strength will be decreased. Temperature and rain, okay, both are related to each other, we already know. Okay, so these are the example of correlation. Please read this, then we move on to next slide. Okay. Now there are several types of correlations. Let me discuss one by one. Generally, we classified correlation in four types. First one, positive and negative correlations, linear and non-linear, partial and total, simple and multiple. So let's see what is positive and negative. Positive correlationship means if both the variables vary in the same direction, then correlationship is said to be positive. In other words, if the value of one variable increases, the value of the other variable will also increase. Or if the value of one variable decreases, then the value of the other variable will also decrease. Then it is known as a positive correlation. And this is the example. The correlation between height and weight of a group of a person is a positive correlation from this data. Here you can see that height is 150, then weight is 58 kg. If height is 157 centimeter, weight is 62 kg. Height is 163 centimeter, weight is 68 kg. So whenever height will increase, the weight will increase with it. Okay, so both will increase together. That's why we can say that this is a positive correlation. In short, if one data will increase, then correlated data is also increased. Or if one data will decrease, then correlated data will also decrease. Then we can say that this is a positive correlation. Okay. And in negative correlationship, opposite to positive. If one will increase, another will decrease. So what is negative correlation? If both the variables vary in the opposite direction, then correlation is said to be negative. In other words, if the value of one variable increases, the value of the other variable decreases, or if the value of one variable decreases, then the value of the other variable decreases. And this is the example: the price and demand of a commodity. So here you can see that price will decrease, but demand will increase. Okay, so both will grow in opposite direction in negative correlationship, and both will grow in same direction in positive correlationship. So there is the difference between both of them. Okay. Correlation might have one doubt. Correlation may or may not have exact ratio of increment or decrement. Yes, maybe they have exact ratio, maybe there are not. If the ratio will be same, okay, then we can say that it is linear. That is the next type of a correlation. But in this type, we only see that both will increase in same direction or opposite direction. Okay. Right now, we have concern with this only. If both will increase in same direction, then we can say that it is a positive. If both are decreasing opposite direction, then we can say that it is negative. Okay. Any other doubts? Okay. Now, linear and non-linear. So now we include the ratio part here. Now what is the ratio part? If the ratio of change between two variables is constant, then the correlation is said to be linear. If such variables are plotted on a graph paper, then it is a straight line is obtained. And if the ratio of change between two variables is not constant, then correlation is said to be nonlinear, and the graph of nonlinear or curvilinear relationship will be curved. So, in this example, you can see that The ratio is fixed in each and every data. For first data, it is 5 by 2. For second, it is 5 by 2 again. For up to last 25 on 10, that means it is 25 5 by 2. Right. And in non-linear, you can see in each and every value, the ratio will be changed. First data, expands is 3 and cells is 8. Right. So ratio will be 3 over 8. Then after, uh, 3 over, sorry, 1 over 2. Then after 3 over 5. So in each and every data, ratio will be changed. That's why it is non-linear. So if ratio is maintained, then we can say that it is linear correlationship. And if you do the graph of a linear correlationship, then it is a straight line. Okay. And if ratio will fluctuate, then we can say that it is not a linear, or we can say it is a curvilinear. And why curvilinear? Because if you do the graph, then it will be curved. In linear, both are in arithmetic progression. Mm, no, arithmetic progression is not required. Okay, just accidentally here in this example, it will satisfy the condition of arithmetic progression. Otherwise, you can arrange it in this form: 5 by 2. Let me write it here: 5 by 2. Here 15 over 6, 15 and 6. Here 25 and 10. Then after you can take 10 and 4, and you can take 20 and 8. So ratio are same in each and every data, but it is not in arithmetic progression. In this example, it is accidentally uh, generated the condition of arithmetic progression. GP. We can say GP. Okay. But AP and GP is included whenever it is a sequence, right, or series. Here this is just a data. So you cannot connect both of these together. We can say GP in that sense that ratio are same, but it is only included when there is a sequence. Right? But it is not a sequence. Any other doubt? In your example, if we rearrange, it is in AP again. In which example? Linear? Look, first of all, this is just a data. Okay, so we cannot connect with it AP and GP. Or second thing is, if you try to connect in AP and GP, AP and GP, then uh, there is no meaning of this. 5 by 2, which you have shown as example. We are compared to data in correlation, and it is same ratio. It's just the meaning of this. It is same ratio. That's why if you do the graph, then it is linear. Okay. There is no sense to connect this data with AP and GP. And if you connect with AP and GP, then what is the meaning of it? It doesn't matter with this. Okay. Any other doubts? So first is positive and negative. Second is linear and non-linear. Right? In positive, both will increase in same direction. In negative, both are increasing opposite direction. In linear, the ratio will be same. Non-linear ratio is not same. Now, simple correlationship and multiple, right? So it is simple. When only two variables are studied, the relationship is described as a simple correlationship, and the examples are the quantity of money and price level. Second, demand and price. So here you can see that we compare two quantity or two variable only, money and price level. Then after demand and price, or in previous example, height and weight, and what we compare, temperature and rain. Okay. So in that example, in all those examples, we compare only two quantity. Okay. That's why it is known as a simple correlationship. Now, if you compare more than two variables, then it is known as a multiple correlationship. Like this, when more than two variables are studied, then the relationship is described as a multiple correlation. And example is relationship of a price, demand, and supply of a commodity. Let me give you another example. Relationship of speed of any vehicle, fuel, and lubrication of oil. Okay. Then after, in rainy season, the rain, if we consider rain as a variable, then rain are correlated with temperature, rain temperature, and let me take a third variable as a greenhouse effect. Okay, all are correlated with each other. So this kind of example represent multiple correlation. And for height and weight, we already discussed height and weight, temperature and rain only. We represent simple correlations. Number of balls, number of runs, and number of wickets. Okay, to give the example, because yesterday we saw the match of IPL. I think I don't remember which match, but balls, runs, and wicket all are correlated with it. We cannot say directly it's correlated with each other. Okay. Any other example? Anyone can give? First of all, give me the relation of a simple correlation. Example of a simple correlation. Let me ask you that. Aditya, can you give me the example of simple correlation?
No, sir. I'm thinking.
Yes, car model and price. Very good. Anyone else? Sudhar, amount of plates and number of guests. Yes, great. And what is the example of multiple correlation? You have to connect more than two variables, right? Anyone? Please, house price, number of bedrooms, and lobby. Yes, perfect. Uses of application and manufacturer. But Ravi, in this example, we correlate only two data, right? Two variables, users and manufacturer. relation between amount of milk and bread per liter. So this is simple. Just for no need more example, but simple. In multiple relationships, there are more than two variables are correlated to each other, and in simple correlation, there are only two variables are related: demand, supply, and price. Yes. Now, total and partial is the fourth type of this correlation. So, what is partial correlation? When more than two variables are studied, excluding some other variables, the relationship is termed as a partial correlation. And in total, when more than two variables are studied without excluding any variable, the relationship is termed as a total correlation. So, what is the difference between different and similarity in partial correlationship? In both these relationships, there are more than two variables. Okay, that is the first similarity in between both of them. In partial and total, in both these relationships, there are more than two variables. But in partial correlation, we include only two and make a relationship or study the relationship between both of them. Whenever in total relationship, we ex- uh, we we include all these variables and make a relationship or study it on every each and every one. Right. So there is a major difference, and similarity is what in both these correlationship there are more than two variables, but in partial we studied only two and excluding except that two. Whenever in total correlationship we studied each and every variable. So these are the types of a correlationship: positive, negative. Positive means growth within growth, or we can say anything, but uh, increment or decrement in same direction of both the variable. Whenever negative, both are in opposite direction. Linear ratio will be same. Non-linear ratio not same. Simple, we studied only two data. Multiple relationship are more than two variable. In partial and total, there are more than two variables, but in partial we studied only two variables, and total we studied each and every variable. So these are the classification. This is the classification of the correlations. Okay. Now next is what? How to studying this correlations. Okay. So first of all, we discuss about what is the correlationship. Then after we classified the correlations. Now method for studying this correlationship. So there are two methods: graphical method and mathematical method. In graphical method, there are two types: scatter diagram and simple graph. Whenever in mathematical methods, there are two types: Karl Pearson's coefficient and Perman's rank coefficient of a correlation. Right. So let me discuss each and every method one by one. First of all, graphical method. And in graphical method, first method is what? Scatter diagram. So what is scatter diagram? Scatter diagram is a diagrammatic representation of a bivariate data to find correlationship between two variables. In this case, the first essential step for calculating correlation coefficient is to plot the observation in a scatter graph or scatter plot to visually evaluate the data for potential relationship or the presence of outlying values. The given statistical data is plotted as point on a rectangular Cartesian coordinate system, taking one independent variable along the horizontal axis, with another dependent variable along the vertical axis. Then we have the following interpretation regarding the nature and strength of correlations. So, what is the difference between scatter diagram and simple graph or simple diagram? Just grab point of each and every data and observe the relationship that is called scatter diagram. Okay. And in simple graph, you join all these points. That is the major difference. Okay. And otherwise, you can represent it on similar way. Just take Cartesian coordinate system. Okay. X as a horizontal axis and Y as a vertical axis. Let me show that. So first of all, perfect positive correlation. If all the plotted points lie on a straight line rising from the lower left hand corner to the upper right hand corner, the correlation is said to be perfectly positive. And this is the geometric representation. Here you can see that all the plotted point rising from the lower left hand corner to the upper right hand corner. Okay, it is in this form, and this is known as a perfect positive correlation. And here I denote r is equal to 1. Now, what is r and why it is 1? That we will discuss later. Okay, just right now, just keep it in your mind that for perfect positive correlation, value of r is equal to 1. Then after perfect negative correlation, if all the plotted points lie on a straight line falling from the upper left hand corner to the lower right hand corner, then the correlation is said to be perfectly negative. It is like this. Here you can see that it is falling from upper left hand corner to lower right hand corner. And for perfect negative correlation, the value of r is equal to negative. Please read this. Then we will move on to next slide. Okay, next is high degree of positive correlation. Now, what do you mean by high degree of positive correlation? If all the plotted points lie in the narrow strip rising from the lower left hand corner to the upper right hand corner, it indicates a high degree of positive correlation. And the graph is like this. Look, perfect positive and high degree both are similar. They increase from lower left hand corner to upper right hand corner. But just the difference is what? In perfect positive correlation, there is only one line. Whenever in high degree positive correlation, there is a strip like this. Okay, and it is from lower left to upper right. Similarly, high degree of negative correlation. If all the plotted points lie in the narrow strip falling from the upper left hand corner to the lower right hand corner, it indicates the existence of high degree of negative correlation, and the graph is like this. Again, it is similar to perfect negative, but in perfect negative there is only one line, and here it is a strip. It is falling from upper right hand to lower, so the upper left hand to lower right hand. The last one is no correlation. If all the plotted points lie on a straight line parallel to x-axis or y-axis or in opposite manner, it indicates the absence of any relationship between the variables. And it's like this. Closed manner means what? It's not arranged in any of the form. So these are the types of a correlationship using a scatter diagram. It is not parallel. No, not every points are parallel, but you can see that this point is parallel to x-axis. Okay. Also, you can find these 2 points which are parallel to x-axis in this way. Okay. It is not like this. Yes. And merits of a scatter diagram. So, what is the advantage of scatter diagram? Let's see. First of all, it is simple and non-mathematical method to find out the correlation between the variables. Here you can see that to define a correlation, you don't need to make any mathematical calculation. Just plot the graph, plotted the point on a graph paper, and you can decide whether it is positive, negative, or no correlation. Right? So it is very much simple and non-mathematical method. It gives an indication of the degree of linear correlation between the variable. So what does it mean by it gives an indication of the degree of a linear correlation? Anyone? Look, the value of r equal to 1 and value of r equal to minus 1. Right. So if value of r equal to 1, then we can say that it is a perfect positive. And in perfect positive, the line is a straight. Right. So using this, we can define it as a linear or not directly. And or the simple observation, you can decide it is linear or not. Okay. Next, it is easy to understand and it is not influenced by the size of extreme items. What what does it mean by not influenced by the size of extreme items? Suppose if you want to calculate the correlation between the data like 4,000, sorry, 44,597, and suppose this is a price, and this is any of the value related to price. Let me say demand. Okay, so for 44,597, the next value is in 5 digit, the next value is in 5 digit, and suppose here the values are in 7 digit. Okay, we consider it is in a gram, that's why it's in 7 digit. Now if you calculate these values using mathematical step, so obviously to calculate this kind of value is very difficult because the values are in 5 digit or in 7 digit. Okay, but if you draw the graph of this kind of graph, suppose you started from 44,000, then you just need to write two lines here. So it is 0, it is 40,000, right? Then after 45,000. Similarly, suppose here it is 7 digits, so 1 lakh, so 10 lakh, and after 20 to up to so on. So using this scatter diagram, you can plot the points very much easily like this, and you can decide it is whether it is linear, non-linear, perfect positive, perfect negative, higher degree positive, higher degree negative, or no correlation. So using scatter diagram, uh, you can draw the graph very much easily, and the extreme size of the data doesn't matter here. Okay, so these are the advantage of a scatter diagram. Please read this. Still, if you have any query, then tell me. Okay, next is simple graph. Simple graph is a diagrammatic representation of a bivariate data to find the correlation between two variables. The value of the two variables are plotted on a graph paper. Two curves are obtained, one for the variable x and one for the variable y. If both the curves move in the same direction, then the correlation is said to be positive. If both the curves move in the opposite direction, then correlation is said to be negative. This method is used in the case of a time series. It does not reveal the extent to which the variables are related. So this is just for your information. It's not very much useful. So geometrically or graphically, we have two methods: scatter diagram and simple. Right? Now next is very much important. That is mathematical method. And to understand mathematical method, first we need to learn covariance. Right? So let's see what is covariance. So before we introduce the mathematical method, let us define the concept of a covariance. Let x1, x2, x1, y1, comma x2, y2, up to xn, yn be n pair of observation on two variables x and y. Then the covariance of x and y is denoted and defined as covariance of x comma y equal to 1 over n summation from I equal to 1 to n xi minus x bar times yi minus y bar. This is the formula of covariance. And what do you mean by x bar and y bar? X bar and y bar is the arithmetic mean of x and y. Okay, and these are the formula. And covariance indicates the joint variation between the two variables. Please read this. And I would suggest in this unit there are so many formulas. Right? I think more than 10 to 15 formula. So I would suggest please list it out all these formula in your notebook. So whenever we solve example, it is easy to recall the formulas if you listed it out. So covariance is 1 over n summation from x equal to 1 to n xi minus x bar times y minus y bar, where x bar is x1 plus x2 plus x up to xn over n, and y bar is equal to y1 plus y2 plus up to yn over n. Now, first one is Karl coefficient of a correlation. Coefficient of correlation is the measure of correlation between two random variables x and y and is denoted by r. And so here you can see that it is denoted by r, which we already uh, write in perfect positive, imperfect negative. In perfect positive, we wrote r equal to 1. In perfect negative, is r equal to minus 1. Now, what is r? R is nothing but Karl coefficient. And what is Karl coefficient? It is covariance over sigma x, sigma y. Now, sigma x and sigma y is what? Sigma x is standard deviation with respect to x, whenever sigma y is standard deviation with respect to y. So covariance is formula 1 over n sigma x minus x bar y minus y bar equal to covariance of x and y, and standard deviation with respect to x is square root of sigma x minus x bar whole square over n, and sigma y is equal to square root of sigma y minus y bar whole square over n, the standard deviation of variable y. Now if you replace all this formula in the form of r equal to covariance over sigma x sigma y, then you will get sigma x minus x bar times y minus y bar over square root of sigma x minus x bar whole square and square root of y minus y bar whole square. Please read this and write both this all this formula in your notebook. Okay, please do one thing. Note down all this formula. I will be back in 2 or 3 minutes. Okay, then we will continue. So this clear now? Any doubt? Anyone? Okay. So now we extend equation one, and we derive another form of a Karl-Pearson coefficient. What is equation one? Equation one is some sigma x minus x bar y minus y bar over square root of sigma x minus x bar whole square and sigma y minus y bar whole square. Now if you multiply x minus x bar with y minus y by numerator, then what you get? You'll get xy minus xy bar minus x bar y plus x bar y bar. Okay. And in denominator, if you expand x minus x bar whole square, then you will get x square minus 2x bar plus x bar whole square and y square minus uh, 2y bar plus y bar whole square. So this type is nothing but like this. Here we expand numerator and denominator of equation number one. Please see that. Now apply summation on each and every term. Summation of xy minus take y bar out of summation of x minus x bar summation of y plus x bar y bar summation of 1 over square root of summation of x square minus 2x bar summation of x plus x bar all square summation of 1 times square root of summation of y square minus 2y bar summation of y plus y bar all square summation of 1. Why we take x bar and y bar outside the summation? Because it is arithmetic mean, right? And arithmetic mean is constant value, so we take it outside the summation. So now replace the value of x bar and y bar in the form of a summation. So x bar is what? X bar is x1 plus x2 plus up to xn over n. So x1 plus x2 plus up to xn, that means summation of x. And similarly for y bar we can write summation of y over n. So replace this value here. Here you can see that summation of y over n instead of x bar. We write here summation of x over n. X bar y bar is summation x over n, summation y over n. Similarly, x bar summation of x over n, x bar whole square summation x over n whole square, summation of 1, that is n, right? Similarly, y bar is summation of y over n, and here y bar whole square, that is summation of y over n whole square, and summation of 1, which is n. Now simplify this. So if you simplify this, you can see here that the summation of 1, this is n, right? So this n and this n will cancel. So remaining terms are summation y summation x over n, summation x summation y over n. So 2 times negative 2 times summation x summation y over n, and here plus summation x summation y over n. So negative 2 minus plus 1, so it will be negative 1 times summation x summation y over n. Similarly here as sigma x over n all square, that means sigma x all square over n all square. So from n square you can cancel 1n from here, and similarly 1n from here. Now what is middle term? Minus 2 sigma x sigma x. So sigma x all square over n plus sigma x all square over n. So minus 2 plus 1 will be minus 1. Similarly here minus 1. So this is the another formula of Karl Pearson coefficient. Just note it down. So what is the difference between previous formula and this formula? Previous formula is this: R equal to, let me, so previous formula is R equal to summation x minus x bar y minus y bar over square root of summation x minus x bar whole square, square root of summation y minus y bar whole square. And this formula is coming out from covariance of xy over sigma x and sigma y. Right. So in this formula, you need x bar, y bar, x minus x bar, x, y minus y bar, x minus x bar square, y minus y bar square. That means you need six data: x bar, x bar, y bar, x minus x bar, y minus y bar, x minus x bar whole square, and y minus y bar whole square. So you need to derive six data. Okay, xy is already given. X bar, y bar, x minus x bar, y minus. Okay, just a second. Now it is clear. Okay. So for first formula, you need to derive six data from x and y: x bar, y bar, x minus x bar, y minus y bar, x minus x bar whole square, y minus y bar whole square. Whenever here you need to derive in this formula, you need to derive x, y is already given, x square, y square, and xy. Okay. So here you need to derive only three data. Now my voice is clear, right? So still it is glitchy. Okay. So here you can see that why we need to derive the another form of calculation coefficient. In second form, we need to derive only three data. Whenever in first form we need to derive six data. That's why we derive this formula. But you need to remember all this. First form is covariance of xy over sigma x sigma y. Second is x minus x bar y minus y bar, and third one is sigma x sigma y. Please note it down. All these three forms. Okay. Then we will derive fourth form of calculation coefficient. Any doubt here? Okay. Now next is the properties. The first property: the coefficient of correlation lies between -1 and 1. That means -1 less than or equal to R, less than or equal to 1. Let me prove this. So first we consider x bar and y bar, which are the mean of x and y, and sigma x and sigma y, which are the standard deviation. Right? So if you generate this equation, summation of x minus x bar over sigma x plus or minus summation y minus y bar or sigma y whole square, then it is obviously positive, greater than or equal to 0. Why it is greater than or equal to 0? Because here we consider square. Right? So square is always greater than, and why it is 0? Sometimes x minus x bar over sigma x is equal to y minus y bar over sigma y. If both the terms are same, then answer will be 0. So it is greater than or equal to 0. Now we apply the expansion. So x minus x bar whole square over sigma x whole square and give the summation separately plus summation of y minus y bar whole square over sigma y square plus or minus 2 summation x minus x bar y minus y bar over sigma x sigma y greater than or equal to c. Now first one is the form of, look, if you recall the formula of standard deviation. So what is the formula of standard deviation with respect to x? The sigma x equal to square root of summation x minus x whole square over n, right? And similarly for y square. So if you replace this formula here, then you will get n plus n. N is from here and n is for second term. Right? Here we take, if you take a square both this side, then you will get sigma x square summation of x minus x bar whole square over n, then n equal to over sigma x whole square. So in this term we replace this term by n. Similarly, you can replace this term by n. Now here you can see that this is the form of a, look, what is r? R equal to sigma x minus x bar y minus y bar square root of sigma x minus x bar whole square square root of sigma y minus y bar whole square. Right. Now if we make subject of sigma x minus x bar whole square only, so here it is sigma x, right? Now in the place we replace sigma x, so what you will get, you can write here sigma x equal to, sorry, if you make a subject square root of sigma x minus x bar square, then it will be the square root of n sigma x. And similarly for this square sigma y minus y bar whole square, that will be square root of n into sigma y. So if you replace both this value here, then you will get x minus x bar y minus y bar sigma x into square root of n sigma y into square root of n. Right. So square root of n times square root of n will be n. And take this n on left hand side. Therefore, nr equal to sigma x minus x bar y minus y bar over sigma x sigma y. So this is nothing but nr, right? So in this step, in this term, you can replace it by nr. So that's why it is 2nr. First of all, please read this. If you have any query, then ask me. Any doubt? This clear to everyone? Okay. Now n plus n plus or minus 2n r. So it will be 2n plus or minus 2n r greater than or equal to 0. Take 2n common. So 2n 1 plus or minus r greater than or equal to 0. That means 1 plus or minus r greater than or equal to 0. And if you open this inequality, so 1 plus r greater than 0 equal to 0. And because of plus or minus, 1 minus r less greater than or equal to 0. That means r greater than or equal to minus 1 or r less than or equal to minus 1. That means the coefficient of correlation set of lies in between minus 1 and 1. So this is the first property. The coefficient of correlation lies between minus 1 and 1. Now property 2, correlation coefficient is independent of change of origin and change of square. Now it is very much important. Now what is change of origin? Let me show you that. Suppose this is a Cartesian plane and we draw x and y axis 0 0. Now first data is 1357. Suppose here we have data 1763. Then after 24327, here it is 3479. So now if you connect all this data, then there is no problem. But if you consider the origin, new origin instead of 0 0, suppose we have origin 1000 or 1200, so it is easier than this. So if you consider the origin as 1000, suppose we consider origin as 1000. So 1357 will convert into 357. 3479 will convert into 2479. Right. Here it is converted into 763. Here it is converted into 1437. So here we change the origin. Okay. Also you can change the scale. So what is the relation between origin? So you can represent in this form: old coordinate equal to new coordinate plus new origin. Okay. Like suppose old coordinate is 1357. New coordinate is 357 here, and new origin is 1300. Okay. So whenever you change the origin, the correlation coefficient is independent from change of origin or change of scale. That is the second property. Right. So let's see that dx equal to x minus a over h and dy equal to y minus b over k. Why we create this formula? So if you simplify this, then it is like this: x equal to a plus h dx, y is equal to b plus dy. Okay. So this is nothing but representation like this. Okay. Look, old coordinate equal to new coordinate. Here it is x and new origin in the form of dx. And h and k represent the change of the scale. So similarly, you can write y equal to b plus k dy. So this is the representation of change of origin. Now, here a, b, h all are constant. So if x is equal to a plus h dx, then x bar is equal to a plus h dx bar, and you can write a subtraction of x minus x bar equal to a will be cancelled, h comma dx minus dx bar, and similarly for y minus y bar is equal to k dy minus dy bar. Now if you replace this formula in equation number 1, what is equation 1? Equation 1 is this. Summation x minus x bar y minus y bar square root of summation x minus x bar whole square and square root of summation y minus y bar whole square is equal to r. Now in this place x minus x bar, here we replace h dx minus dx bar, and here in place of y minus y bar we replace k dy minus dy bar. So let's see what happens. So if you replace this in this form, so this is the formula for xy only, right? Now in place of x minus x bar and y minus y bar we replace this formula. So you can see here that h square, if you take it outside the square root, then it will be h. That is also k. H and k both will be cancelled. So formula is this. Now if you compare this and this formula, both this formula, then instead of x, here we replace dx. Instead of x bar, we replace dx bar. Instead of y, we replace dy, and instead of y bar, we replace dy bar for each term. Right. So this is nothing but this is the formula for x and y. Then this is the formula of dx and dy. So here you can see that r of xy equal to r of dx dy. So old origin is x, but new origin is dx. Old origin is y, and new origin is dy. Exponent and y coordinate origin, right? So here you can see that change of origin does not affect on correlation coefficient. Dx is a new origin. True. H is a change of a scale. Suppose you have origin like data like 1 lakh, 2 lakh, 3 lakh, 4 lakh, 5 lakh. Okay. So if you consider H as a tenth of, okay, then you can generate the new origin like this: x minus a over h. So if you divide it by h, the value will be decreased. So H and K represent change of a scale. Using H and K, you can convert largest data into smallest. So Rxy is equal to R dx dy. So this is the first form. Now what is the second form of the Karl Pearson coefficient? We already see that. That is summation xy minus summation x summation y over n. So this is for x, y, and y, but then after we already discussed the second form. If you replace all this value in second form, then you will get this formula. Okay. Second form is what? Second form is like this: summation xy minus summation x summation y over n over summation x square minus summation x whole square over n summation y square minus summation y whole square over n. Now in this form, in the place of x, if you replace dx, in the place of y, if you replace dy, then you will get this. Second property is what correlation coefficient is independent of change of origin and change of scale. Please note it down these two formula. This is also very much important formula. So up to this property, we show total five formula of Karl Pearson coefficient. First one is very basic formula, covariance of x, y over sigma x, sigma y. Then after this form, then after this form, then third one is this. This is a fourth one, and this is a fifth one. So there are total five formula for correlation coefficient, Karl Pearson correlation coefficient, and that is it is clear to everyone. Anyone have a doubt? Please for other students. Okay. Yes, so this is it for our today's session, and we will discuss the next concept